For the longest time, the story of AI has been pretty simple. Bigger is better. Bigger models, more data, huge computer clusters. But what if? What if you could get shockingly close to top-tier performance with just one graphics card in just one day? Okay, let's dive into this fascinating experiment.
So let me ask you this. Do you really need a supercomputer to train a powerful AI from scratch? Well, today we're digging into a research paper that throws that whole idea into question, basically asking, how far can we really get on a shoestring budget?
All right, here's what we're going to cover. First, we'll look at this kind of expensive arms race going on in AI. Then we'll dive into this one-day GPU challenge. We'll see how they hit a major wall, what their secret recipe was to get around it, check out the results, which are pretty wild, and finally we'll talk about why any of this actually matters. First up, let's set the stage. The world of AI training right now, it's become a battle of giants, a real Goliath problem.
Okay, take a look at these numbers and just try to wrap your head around the scale here. In exaflop, that's a billion calculations. The original BERT model, 680 of those. Google's PaLM, a whopping 7 million. Now, look at the bottom line. The budget for this cramming experiment was between 5 and 13. That's not just a step down, right? That's a completely different planet of computation.
And, this has created this really powerful belief in the field. It's almost a mantra. If you want better AI, you just make it bigger. More data, more compute, more everything. And look, it works. But it also means that almost nobody can play the game unless you have a massive corporate or government level budget. So yeah, this is the perfect setup for a classic underdog story. A real David emerges to take on the Goliath of big AI. So the researchers came up with what they called the Cramming Challenge. And the goal was, well, it was simple, but also kind of nuts. Train a language model from absolute zero on a single GPU in just 24 hours. Think about it. It's like trying to cram for a huge final exam for a class you've never been to all in one night. And to make it a fair fight, they set some really strict rules. Rule 1, you have to train the model completely from scratch, no shortcuts. 2, no using parts of other pre-trained models. That's cheating. 3, any raw text data is fair game. 4, and this is the big one, all the training has to happen on that one GPU, and the clock stops at 24 hours. And finally, the big test. Its performance is judged on the GLUE benchmark, which is a standard academic test to see how well it understands language. Okay, but it's not as simple as just shrinking a model and calling it a day. The team immediately slammed into this fundamental problem in AI, this thing we can call the scaling wall. This wall is built from something called scaling laws, and the principle is pretty straightforward. A model's performance is predictably tied to its size. But here's the catch, and it's a big one. Smaller models are just dumber learners. They're less efficient. So yeah, they might process data faster, but they learn so little from each piece of information that it basically cancels out any speed advantage they had. It's a real catch-22. And this chart right here illustrates the problem perfectly. You see all those different colored lines? Those are all different model architectures. But look at them. They're all following the exact same downward curve. What that tells you is that just tinkering with the model's shape won't let you cheat the system. A model with 1 billion parameters is just fundamentally a better learner than one with 100 million. End of story. So here's the takeaway. The crucial point is just making the model smaller isn't going to cut it. You have to figure out a way to make it smarter, to make it train more efficiently, and squeeze every last drop of learning out of every single second. So how did they do it? That brings us to their solution. Let's break down the secret ingredients that made up their cramming recipe. They found a loophole, a really clever one. If the learning efficiency is basically locked to the model's size, then the only way forward is to keep the model pretty big, but find all these clever tricks to speed up the computation itself. The goal becomes, how can we process more tokens per second without having to shrink the model down to nothing? Okay, ingredient number 1 was a smarter architecture. They made a bunch of small, almost surgical tweaks. For instance, they got rid of biases, which are like these little nudges in the network's math, and they used techniques like pre-normalization to keep the whole training process from going off the rails. Now, each one of these changes is tiny on its own, right? But together, they shaved off precious microseconds from every single calculation. And when you're running for 24 hours straight, those microseconds add up to a lot. Ingredient number 2,
a super aggressive training schedule. I mean, they were really pushing it. They used what's called a one-cycle learning rate. It just shoots up really fast and then comes back down. They started with small batches of data and then ramped up the size as they went. It's kind of like they just slammed the gas pedal to the floor right from the start, trying to make as much progress as humanly possible, as fast as possible.
Now, one of the most interesting tweaks, and it's a bit counterintuitive, was disabling dropout. See, normally, dropout is like a safety feature. It stops the model from just memorizing the training data instead of actually learning. But in this case, the bottleneck wasn't a lack of data, it was a lack of time. So turning it off was this calculated risk that let them maximize the number of updates to the model every single second. And the third and final ingredient? It's simple: better data. They switched to a much higher quality data set called the pile. They filtered out all the messy junk like chaotic HTML code, and they even sorted the data so the model would see shorter, simpler sentences first. The logic here is just common sense, right? If you're on a super tight deadline, you better make sure that every single thing you study is as high quality and useful as possible. All right, so they've got this clever recipe: smarter architecture, aggressive training, better data. They put it all together. How did their little crammed model actually do? Let's get to the verdict. And honestly, the results are just wild. On the GLUE benchmark, a fully trained BERT-based model, the result of a massive multi-day, multi-GPU training run, it scores an 81. The model they crammed onto a single GPU in one day, it scored an 80.4. Let that sink in. They got over 99% of the performance with just a tiny, tiny fraction of the resources. That's incredible.
Even the researchers themselves seemed a little shocked. In their paper, they said the performance was surprisingly decent. And let me tell you, in the super understated world of academic papers, that's basically like shouting from the rooftops that you've done something amazing.
Okay, so this is way more than just a cool science experiment. This has real implications. Let's talk about why this actually matters and what it could mean for the future of AI. What this cramming recipe really does is it provides a roadmap. All of a sudden, real, meaningful AI research becomes accessible again for smaller labs, for universities that don't have bottomless pockets. It means an organization could actually train a model on its own private, specialized data without needing a supercomputer. And maybe most importantly, it just opens the door for so many more people to innovate and experiment in this space, not just a handful of giant tech companies.
And that really leaves us with this final, and I think really exciting question. For years, we've seen what a few massive labs can do with what seems like infinite resources. But what new ideas, what incredible applications, what new discoveries are we going to unlock when pretty much anyone can build and train a powerful AI model right from their own desk?